All right. So this is a joint work with José, Bacelar, Almeida, Tiago, Oliveira, and Dominique Unruh on leakage-free probabilistic programs in Jasmin. So let's start with the motivation. Let's imagine the following toy system. So we have a server, and this server keeps a secret, which it is willingly can give away if you guess a password. And the password is sampled uniformly at random, and is 256-bit string. And let's assume that the only possible attack vector for the adversary is to guess the string. So for such a simple toy system, we can actually prove that it has kind of a galactic security. So the probability that adversary guesses and gets the access to the secret are negligible. At the same time, it's worth saying that for real systems, security might crucially depend on the implementation details of the server, even such a simple one. For example, the optimizing compiler might decide to generate machine code which checks equality between the secret and the guess until the first difference is encountered. And in this case, if adversary can time responses of our server, then it can figure out the secret in a byte-by-byte fashion and steal the secret during the lunch break. So what we're having is we have a discrepancy between the predictions of mathematical model and the real-life implementation. And this illustrated attack belongs to a family of side channel attacks, which include such attacks as timing, cache, and power analysis attack. And so the challenge which we tackle here is the question on how to prove that an executable of an actual protocol is correct, cryptographically secure, and is free of side channel attacks. And we would like to do this all at the same time within the same environment. So one way of doing this is to use Jasmin programming workbench, where Jasmin is a programming language which combines high-level and low-level constructs to support so-called assembly-in-the-head programming paradigm. So programmers in such paradigm have access to low-level features like instructions, scheduling, registers, stack, but at the same time it has natural access to the high-level abstractions like functions, arrays, loops, and so on. Let's look at the overview. How do you work in Jasmin? So the important thing is that Jasmin code can be extracted via compiler to the EasyCrypt theorem prover with leakage annotations, where leakage annotations accumulate all the informations which attacker can get to through side channels. And in this work, we focus on timing attacks, but everything which we say is not specific to timing attacks. It can be generalized to any side channels. And originally, in Jasmin, the leakage analysis was only performed on deterministic programs, and recently it was extended with some sampling primitives. And so we would like to see how to prove formally absence of side channels for probabilistic programs. So let's look at the example. So here on the right, you see a program which tries to sample a bit uniformly at random. So you see some details, but the really important part is that we're using the built-in primitive random bytes to get a random byte, and then we're just checking if the sample byte is smaller than 128, in which case the result is 0, and in other case the result is 1. So here the important thing is that we have no inputs, and we would like the output to be secret. Now by using the compiler, we can extract this code to EasyCrypt theorem prover, in which case it generates a module with a procedure where all the constructs from the Jasmin were translated, but at the same time, the code is annotated with leakages. So now you see that at every step we're accumulating some leakages, and this is over approximation of what kind of information adversary can get if they would time the program. So the highlighted leakage annotation in red is actually the problematic one. So it happens because of the conditional which we use, and as you see, it leaks the Boolean which goes into the conditional. So in principle, if adversary has access to that information, then they know fully what is the output, what is the secret output of the program. So we can try to do better and change the program slightly, in which case, instead of doing a conditional, in the same fashion, we sample a byte, and then later we just do the bitwise AND of the result with the number 1 and return it. So in this case, if we instruct compiler to produce the leakage code with the leakage annotations, then you can see that intuitively the result of the execution and the leakages which are produced are independent. So the challenge is how to formally prove that probabilistic program is free of leakages. Before answering that question, we can look at the prior definitions from the literature, where we can, and more specifically, so-called cryptographic constant time programs. So for this definition, we assume that F is a deterministic total program in Jasmin, and then when it's extracted, then we compare these two probabilities. So the program F, it depends on it has public inputs and secret inputs SYN. Checking equality of probabilities which are produced for particular leakage, we're asking whether the leakage is produced in one case. Hello? Oh, now it works. Okay. Oh yeah, I think now it works.
Okay, cool.
Yeah. So for most of the programs for which this property holds, the cool thing is that it can be derived fully automatically by using the simulation tactic. But the question remains whether it's an adequate definition for the probabilistic programs. Here, the important thing to notice is that what intuitively this definition does is it checks whether the leakages depend on the secret inputs. So in the first probability expression, the second probability expression, the secret inputs are different. So if this probability are the same, then intuition is that leakages are independent of the secret inputs, in which case we can say that it's cryptographic constant time. Okay. But let's look at our naive bit sampling. And then we immediately see that since there is no inputs to this function, then the previous definition is trivially satisfied. So the output, in a way, the output which we produce in this procedure is being generated. It does not depend on any secret inputs, but kind of is generated within the computation inside the procedure. So this definition is no good for probabilistic programs, and we must generalize. To do that, we propose a kind of semantical characterization of leakage-free programs, where we define two probabilities. The probability W is a probability of producing a particular output A, where the probability V is a probability that we generate the output A and the leakages L. And then we say that the program F, which is a total program, but now might be probabilistic, that for some there exists a function G and compute probability V divided by W. So given that we produce an output A, the program produces also the leakages L, and that this conditional probability depends only on the public inputs and the leakages. So we are not allowed to access the secret inputs during the computation of this conditional probability. The important thing here is that for most of the cases, this definition is really annoying to prove because it's existential in this computation of the conditional probability. So for most of the cases, it would be hard to apply. But the good thing about this definition is that it's inspired by probabilistic non-interference, so it has really clear it has really clear semantics. For example, for our program random bit, which is very simple, we would be forced to define the function g, which inside has to define a constant which is actually fully describes the leakages which are being produced during the computation. So in some sense, any change to this procedure would break the proof of leakage-freeness, and you'll have to go and, again, characterize the accumulated leakages differently, which is very suboptimal for big actual cryptographic primitives with which we are working. So the next challenge is, can we define a probabilistic leakage-freeness in the equivalent but somewhat auto-provable way? And for this, we give this definition number 3, which is phrased in terms of probabilistic relational Hoare logic, which relates to programs. So the program on the left is just a single run of the function f, which produces the result r and the leakages as it's supposed to. The program on the right is a little bit different. So first, it runs the program f in the environment where it generates only leakages, but we ignore the result. And then at the same time, we run this program again, but without generating a leakages, but only generating the result. And the statement says that if for such programs we start in the same state, and then they produce the same leakages and the same result, then we can claim that this program F is leakage-free. The good thing about the number 3 is that, again, we restored the of the programs. It's going to be easy to prove by just simulation tactics provided by EasyCrypt. So we are in a good shape. This is the example of such proof. This proof is not going to change if the program on the right will be too much different. So the only thing which happens here in the proof script is that it sort of runs the simulation of the program in the PRHL. The important properties, which is the main contribution of the paper, is that we show that definition 2, semantical characterization, and the PRHL characterization, definition number 3, are equivalent. Moreover, the second property says that it's actually a generalization of the constant time. And moreover, for deterministic programs, both definitions, the constant time and then probabilistic characterization, they coincide. The hardest proof in this formalization was actually the proof of the compositionality. So we proved that if you compose two programs which are individually leakage-free, then they produce a leakage-free program. But we tried to push the limits and actually apply these definitions for somewhat more complicated use cases. And for that, we decided to study rejection sampling. For those who are unfamiliar, so rejection sampling is the approach to create probabilistic distributions out of some given prior distributions. In our case study, what we took is that we have a primitive which generates distributions whose cardinality are powers of 2. And then the goal was to generate distributions of uniform distributions of arbitrary size. The goal is to prove that this is actually leakage-free. The challenging aspect for this program is that the algorithm doesn't have a priori termination bound, which means that it only terminates with probability 1, but we don't know the upper bound on how many iterations it is gonna run. And then actually for such programs, it turns out that for both definitions, it's challenging to prove leakage-freeness. So for definition 2, we actually need to fully characterize the structure of leakages. So it has to be an explicitly defined function which depends on the number I, where I is the number of iterations. And for the third definition, a pure shell characterization, we need to use some clever tricks based on Bernoulli distribution, where we need to detach generation of the leakages from the generation of the actual output. Moreover, another challenge which remains for these definitions actually proofs of leakage-freeness for non-terminating programs. So everything which I said so far was only about programs which terminate at least with probability 1, but for non-terminating ones, the problem is still open, at least in the setting of Jasmin. And this brings me to the conclusions. So what we did is we defined two novel and equivalent definitions of leakage-freeness for probabilistic Jasmin programs. We showed that they generalize the previous cryptographic constant time notion. We also proved that these are compositional. We showed on some use cases that PRHL definitions for most of the programs which do have a priori termination works really well with the simulation tactics and can be proved automatically. But still, for programs with no a priori termination at time, both characterizations are tricky, and the question on non-terminating programs is still open. And that's it.
Are there any questions?
Thanks for the talk. Can I go back to definition 3?
Yeah. Yeah, sorry.
Yes. So in PRHL, the way you prove these equivalences is by tactics that allow you to align the samplings on both sides and then use a coupling rule, right? But there you have two programs on the right-hand side, one program on the left. So you're going to have twice as many samplings on the right.
Sorry, I don't really hear you.
So when you prove equivalences in a PRHL, you align the samplings on both sides.
Yes.
But usually. But there you have twice as many samplings on the right. Can you say a bit more about how these proofs work?
Oh, yeah. So, I mean, here, the important thing maybe, which I only briefly mentioned, is that, so here, the first invocation of the program, it only generates the leakages, and we fully ignore, so it's a distribution of the leakages. But the result is ignored of what it's produced. While on the second run, we ignore the leakages, so leakages are not produced, but the result is produced. So in a way, you have a fully two detached computations where one first run of it generates leakages, and second one generates the result, and then independent. The important thing here to see is that when we produce the leakages, then the secret inputs are different. So we're producing leakages out of the secret inputs which are different from the program on the left. So that's kind of ensures the difference between. So I mean, it ensures that leakages do not really depend on the secret inputs in this case.
Okay, maybe I'll ask later because I asked it and yeah, thanks.
Maybe this is just a clarification of that previous question, but what is XTRI in this?
XTRI is the same program, so it's the equivalent program to F, but the one which does not generate leakages.
So you just automatically generate two versions of every program?
It's a compiler-produced program which is equivalent to the Jasmin program, but just without leakage annotations. Yeah.
Can you go back to the definition 2,
yes,
please? Right. Here you quantify about the secret input, the private input, but also about this M. What is the M referring to?
Sorry.
The M in bold.
Oh, M in bold. So this is the initial state of the module, which, I mean, in this case, it's not too relevant because for the standard Jasmin, there is no global variables. So, I mean, but technically speaking, it quantifies over the initial states of the program. And then, I mean, for both of those, the initial state is the same. But the only place where it plays the role is that we're saying that the leakages on the both sides for both of the cases are the same. And then, I mean, it can start from the arbitrary leakages, and that helps with the compositionality. So, I mean, we start from any state with any leakages, and then we only prove about the extension of this accumulator of leakages.
Hi, so I was wondering if this definition already encompasses the possibility for there to be a small difference between the probabilities of the leakages, because the way that G is quantified, you might have a bit of wiggle room. So I'm wondering whether you considered sort of a computational indistinguishability style definition here.
We didn't.
Okay.
Yeah, but I mean, the important thing is that it's kind of, I mean, I think for different people, maybe either definition 2 or definition 3 is more intuitive of what's actually supposed to be idea behind the leakage freeness for probabilistic programs. And for exactly those definitions, I mean, we show that the equivalence. So, I mean, it's a very fragile property to keep.
Yeah, makes sense. Thank you.
Yeah. Do you have any consideration for like the non-determinate, like if you have a function which is generating randomness,
yes,
but the randomness distribution doesn't depend on the secret? Like, is that covered under this?
Sure. I mean, that's a simpler case. Maybe I misunderstand the question, but
well,
I mean, if your distribution does not depend on the secret input, it's, I mean, we cover even the cases where it will be like, you know, where it will depend in some non-obvious way. But if it's obviously doesn't depend on the secret input, it'll just.
Well, like for the same secret, you might get different values out.
Yes.
But then with a different secret, you also get different values out, but the distribution, like it's not constant time, because it.
Yeah. Here there is nothing about actual. I mean, about the constant time in terms like of the like canonical classical definition of constant time. It's really, I mean, what you're comparing is for this definition, since the program is probabilistic, the leakages are also distributions, which depend on the public inputs and the secret inputs. And then what you're comparing is two different distributions of leakages.